All right, welcome everybody. Thanks for joining today. I wanted to talk about the equational form of a linear program. So there are many different adjectives that you can use to describe forms in which you put a linear program. Maybe it's the standard form or the equational form, canonical form, normal form. There's many different adjectives. I don't want to use too many of those adjectives. I want to just use one, the equational form. And that'll be the main form that we focus on because it's the form that's needed for the simplex method. First, let me talk about a different form. The only name you need to know for this form is that it's not the equational form. But this is good practice. So I want to describe how any linear program can be rewritten in the following form. Maximize C transpose X, subject to AX is at most B, where C is a vector of weights on the function we're trying to maximize. X is our vector of n variables. A is our matrix encoding all of the constants that appear in our constraints. And B is the vector giving the right-hand side of our constraints. So as we'll see in a moment, in this problem, we have n variables given by vector x of length n, and we have m constraints given by the m rows of matrix A or the m rows of vector B. So in this particular form, we want to have a maximization problem, and we want all of our constraints to be inequalities. So I have no equality constraints. Furthermore, all of our inequalities are less than or equal to's. Okay, so let's put this sample linear program into this particular form. The first thing I need to do is I need to change my minimize into a maximize. And that is always easy. You just multiply the function that you're optimizing by -1. Because making 3x1 plus 4x2 as small as possible is exactly the same as making -3x1 minus 4x2 as large as possible. Okay, now let's turn our constraints into the proper form where they're all less than or equal to constraints. So this first greater than or equal to constraint, I just multiply by -1 to get a less than or equal to constraint. And the inequality flips sides. This equality constraint right here, I turn into two inequality constraints. So that's equivalent to saying that x1 plus x2 is at most 3. And furthermore, x1 plus x2 is at least 3. But I don't want greater than or equals 2's, right? I only want less than or equal 2's. So instead of writing x1 plus x2 is at least 3, I'm going to multiply that by -1 to get -x1 minus x2 is less than or equal to -3. Logically, that's the same as saying that x1 plus x2 is at least 3. And then combining that with x1 plus x2 being at most 3, we get x1 plus x2 is exactly equal to 3. So let me put this in matrix form for you. What is our optimization vector C? It's -3, -4, coming from right here. And then our vector x of variables is x1, x2. Our matrix A, I'm just going to read off the coefficients on this side. So -2, 1, 1, 1, -1, -1. And our vector B, I'm going to read off here. -2, 3, -3. N is the number of variables. That didn't change. M is the number of constraints. That increased by 1. right? We went from 2 constraints to now 3 constraints. So we got down to 3 constraints. Okay, let me do this one more time. Let me just show you how C transpose X and AX at most B, namely these expressions, recover these systems of equations. So C transpose X, in this example, I take the transpose of this vector, so I write it sideways, and then I do matrix multiplication with x1, x2, and I get -3 x1 minus 4 x2. Okay, so C transpose X indeed recovers the thing we're maximizing. And let's do this again with AX at most B. So AX is this matrix, -2, 1, 1, 1, -1, -1, times my vector x1, x2. I multiply that out, I get -2 x1 plus x2, x1 plus x2, negative x1 minus x2. Okay, to say that this is at most B would be the following. Our vector B is -2, 3, -3. And when I write one vector is at most another, I mean that entry-wise. So looking at the first entry gives me this first constraint, and then looking at the second entry gives me the second constraint, and similarly for the third constraint. Questions? Okay. That's the warm up. Let's get to the meat. The simplex method requires a different form called standard form. That's maybe the term that most people use. Our book uses the word equational form. Okay, so standard form, equational form mean the same thing. And we'll just try to call this equational form. And hopefully it's the main name that I want you to memorize about forms of linear programs. So it's written right here. You're trying to maximize C transpose X subject to AX equals B, and all of our variables are non-negative. Okay, so it's almost like the majority of the constraints have been changed to equalities. And to do this, we're going to have to introduce new variables, which are called slack variables, and are quite important. So the interesting or the main constraints are equality constraints. But don't forget about this non-negativity. The non-negativity is really important, and it's saying that every variable is non-negative. So not just some, but all of the variables are non-negative. You can transform any linear program into this form. Your linear program could have some but not all non-negativity constraints. It could have greater than or equals 2's. It could have less than or equal 2's. And we're going to put it into this precise form. So I'm explaining the algorithm for how to do this in general, but I'm only doing that while on this one particular example right now. But this example contains all the tricks that you need to know to take any linear program into equational form. Okay. So first, what we're going to do is our less than or equal to constraints. We're going to turn them into equality constraints by introducing what are called slack variables. So 2x1 minus x2 is at most 4. That is a less than or equal to constraint. We're going to let x3 be a new variable, right? In our original problem, there's no x3. We introduce what's called a slack variable, x3, which really encodes how far this inequality is from being achieved. So x3 is just the extra gap. x3 is just the difference for minus 2x1 plus x2. Okay, so when I add in the slack, then my former inequality becomes an equality. Do you see that? x3 is just the leftover. You know, x3 is just 4 minus 2x1 plus x4. And we add in this non-negativity constraint. We always want the slack to be positive, non-negative, because if the slack were negative, then our inequality wouldn't be satisfied. Right? Questions so far? This is the key. At first, it seems hard to turn inequalities into equalities. And it is. And the only way, or the way we do this is by introducing an extra variable called the slack variable.
Hey, Henry. Oh, never mind. You erased it. Never mind.
Sorry. Oh, wait. It's back.
Oh, it's just, I think it's supposed to be x2 instead of x4.
Wow, thank you.
Sorry, you were erasing it anyway.
No, I appreciate it. Because once something's on the internet, it's on there forever, right? Oh no, I wrote it wrong again. Oh my goodness. Okay.
So just to make sure, this circled thing is not a new parameter or thing we're subjecting to. That's just like our mental idea of what x3 is.
That's right. I'm about to delete that. I'll leave it here for a couple of seconds longer to correct my mistake. But yeah, this is not part of our new linear program. What we will do though is we will get rid of this constraint and replace it with these two. Okay. Thanks, Shannon, and I think Shannon, yeah, and Kyle for the help. All right, what do you do with a greater than or equal to constraint? Pretty much the same thing you did with a less than or equal to constraint. First, turn your greater than or equal to constraint into a less than or equal than constraint just by multiplying by -1. And then add in a slack variable. Okay, so x4 is going to be the slack in this equation. x4 is non-negative, and it tells me how far this equation is from being satisfied with equality. So once I add that in, it becomes an equality, and x4 had better be non-negative so that our original inequality was satisfied. I might have had equality constraints. You know, I might have had like x1 minus x2 was equal to 5. Those I don't need to change, right? Because I'm trying to get to a form that allows equality constraints. So equality constraints you just leave be. There's one more thing we need to do, which is the following. In equational form, every variable has to be non-negative. I'm missing that here. x2 is non-negative, but x1 is not non-negative. So in some sense, I want to add in the constraint x1 is non-negative, but I can't just add it in like that because that might change my feasible set, right? So to handle this missing non-negativity constraint, right, x1 is a variable that's not constrained yet to be non-negative. Here's how we do it. We're going to write x1 as the difference of two non-negative variables. I'm calling them x1 prime and x1 double prime. Both are going to be non-negative. Okay. So if x1 were positive, you could, let's say x1 were equal to 3. You could just simply let x1 prime be 3 and x1 double prime be 0. Okay. Let's say x1 were -5. Then you could let x1 prime be 0 and x1 double prime be 5. right? So x1 and x1 prime and x1 double prime are always going to be non-negative. But by subtracting two non-negative numbers from each other, you can get an arbitrary real number. Okay, so everywhere x1 appears up here, we're going to replace x1 with x1 prime minus x1 double prime. We're going to substitute this in everywhere we can and for x1. So 3x1 becomes 3x1 prime minus 3x1 double prime. This 2x1 becomes 2x1 prime minus 2x1 double prime. Minus x2 stays around. And then I have my slack variable, x3. And my slack variable took this inequality to an equality. And x1 became, oh, right, okay. This inequality became this, okay? And then negative x1 becomes negative x1 prime plus x1 double prime. Negative 3x2 comes along for the ride. I have my slack variable and I have my equality. And I have all the non-negativity constraints. So x1 prime and x1 double prime are non-negative. x2 is non-negative. And my slack variables, x3 and x4, are non-negative.
Is there a specific name for the variables x1 prime and x1 double prime? Are they slack variables?
I would not call those slack variables. I don't know a name for them. Does anybody know a name? Yeah, I'm not sure, but I would not call them slack variables. Yeah.
It's interesting to me that the prime variables are non-unique to represent the original variable.
Yeah.
Does that matter? I mean, obviously it doesn't matter because you end up getting the x1 that you want, but in some sense your feasible set can shift around, I suppose. Perhaps might be a way to look at it. I'm not sure.
Yeah, so I might describe it as follows. So first of all, okay, so everywhere that up here in our optimization function and in our constraints, everywhere that x1 prime appears, it appears right next to a negative x1 double prime, right? So they never really matter on their own. So you're right, there is extra redundancy. You know, instead of letting x1 prime and x1 double prime be something, I could shift them both together and let them be something else. But that doesn't improve my optimization function, right? Nor does it change whether I've satisfied any of the constraints or not, right? So I would think of this, it's a little bit like by adding another variable, we're adding another dimension, right? So maybe our original problem was in the plane. We were trying to optimize over some convex region in the plane. Now it's like we're doing this in 3D, okay? But in 3D, you know, it's like our feasible region in 2D might have been a square, and now in 3D, our feasible region, I just take I translate that, so I get like a, you know, like a square pillar that extends forever, right? Yeah. And our optimization direction was pointing somewhere in the plane, and it's still sort of pointing that same way in 3D.
Yeah, that makes perfect sense.
It's an approximate visual, yeah. Other questions? This last step really doesn't matter, but I want you to be comfortable with it. Then we're just going to relabel the variables. The common names for variables are just x1 up through xn. And so we don't want to have these primes and double primes floating around anymore. We just want to ignore those. So I'm relabeling the variables, right? So it's confusing because x2 is being relabeled as x3, and x3 before meant something different, but it's just changing names, okay? So if I wanted to write this in like the final equational form, I'd be maximizing 3x1 minus 3x2, because I've relabeled x1 double prime as x2. Okay, minus 2x3 subject to, I should write this a little bit more cleanly, subject to 2x1 minus 2x2 minus x3 plus x4 is equal to 4, and negative x1 plus x2 minus 3x2. Oh, that should be an x3 because it got relabeled. Plus x5 is equal to negative 5. And all of the variables are non-negative. Okay. What's critical is that you believe that if you could solve this problem, right? If you can solve this problem, find the optimal x1, x2, x3, x4, x5, then you change those back into x1 prime, x1 double prime, x2, x3, and x4. And then you change those back just into x1 and x2. Okay, so we've added a lot of variables. We've gone from 2 variables up to 5. But we've put our linear program into this very particular equational form where all of our constraints are equalities and all of our variables are non-negative. Let's complete this story. So our vector C is coming from optimization function. So it's 3x1 minus 3x2 minus 2x3 plus 0x4 plus 0x5. Our vector x of variables is x1, x2, x3, x4, x5. Our matrix is a 2x5 matrix with coefficients 2, negative 1, 1, 0, and negative 1, 1, negative 3, 0, 1. Our vector B is 4, negative 5. And the new number of variables is 5. We went from 2 variables up to 5. M, the number of constraints, is 2. And then we also have, M is the number of equality constraints. And then we also have all of the non-negativity constraints. So these are the vectors and matrices putting it in equational form. You might be worried that when you put your linear program into equational form, maybe you get an exponential number of constraints or an exponential number of variables in terms of what you started with. And that'd be a problem because that would, take fast algorithms into exponential ones. But you don't. You use the number of new variables and constraints you get is linearly bounded by the number of variables and constraints you started with. So pretend we started with n variables, above it was 2, and m constraints that were either less than or equal to, bigger than or equal to, or equality. So above, I think we started with 3 constraints, a less than or equal to, a greater than or equal to, and a non-negativity. Okay. You always end up with at most m plus 2n variables. So we originally had n variables. Those all stick around. You get an additional n because any variable like x1 up above, which wasn't bounded to be non-negative, can give you x1 and x1 prime and x1 double prime, okay? So from our n variables, we can get an additional n coming from this non-negativity. And each constraint can give us a slack variable, okay? So I went from n variables to n plus m. The plus n was from duplicating an x1 into an x1 prime and x1 double prime. And the plus m was coming from every constraint could have given me a slack variable. And then you don't expand the number of constraints in some sense. From our m constraints, we get at most m equations, maybe exactly m equations, along with all non-negativity constraints. So in any case, you don't get this exponential explosion from n variables and m constraints. This procedure gives us a linear number of variables and constraints. So let me emphasize again, this is worth reviewing. Slack variables will certainly come up again. And I'll put this as a sample homework problem that you could choose to do. But it's important to be comfortable taking any linear program, putting it in equational form. All the constraints are equalities, except for our non-negativity constraints on every single variable. To plug a linear program into a computer, you typically don't need to do this, right? You can give a computer whatever constraints you want, but this is the first step your computer will do. It'll turn it into equational form. Questions? Thanks, everybody.